Uli. Thanks a lot, Uli, for the nice introduction. And maybe a short word for the start that this talk I was asked to give was basically initiated when I gave a similar talk at TU Berlin, which was more on a student level. And then I was asked by Robert that I should possibly bring this here. So I feel very honored to be invited to do so. So let me now share my screen. Can you see my screen?
Yes. Now we see the screen, but still not in the presentation mode. No.
No.
Yeah. Now it's fine.
Okay.
Yes.
So I was aiming to speak about the story of the North German Basin and its potential for today. And you see here a number of co-workers that have been working with me over the past, let's say, 15 years on the North German Basin or the Central European Basin system. But of course, this work rests on the shoulders of a lot more. Especially in Hanover, there were a lot of basic work done to have the basis for doing this, what I will present today. So let me first put the North German Basin into its plate tectonic setting. It's, of course, an intracontinental basin, and it's part of the Central European Basin System that you all are probably very familiar with, extending from the North Sea to Poland. And to make my main message clear from the beginning, today and over the largest part of the past 260 million years, this area is a flat, slowly subsiding place. So it's basically most of the time continental fluvial lacustrine deposits are accumulating. We have a bit of a change between arid and humid periods, and these are interrupted only by very few marine episodes that are connected to global sea level changes. So we see to the right the Elbe and the Havel landscape, and this is a bit similar to what the North German Basin was like over a lot of its lifetime. So how do the 266 million years look like, or how does the record of these million years look like? To find out, what we do is what we call a database strategy in our section. We use data-based models that integrate a lot of different data. We run dynamic simulation based on these structural models to build some multi-parameter digital twins. And we do that on the scale of basins, of origins, or of georeservoirs. The tools we are using are mostly free and can be downloaded or accessed. And I put here the address, the website where you can get to them. So what do we mean if we say integrating observations in 3D geological models? We really mean all types of data that we can get hold of. And that goes from the seismic to the field to wells, potential fields, but also other independent observations such as seismicity or tomography increasingly at different scales for the mantle, for the crust, seismology in all its shades, and in more recent times also geodetic observations. For the North German Basin, we are in a very fortunate situation because it was a place where there was petroleum exploration for a long time. That's why we have a lot of data. And what you see on the upper left of this picture is basically compilations that include all kinds of seismic data. Wells have been compiled by national groups or by federal countries. And of course, the work of the BGR and of the Niedersächsische Landesamt für Geowissenschaften is included here. You see an example of such a section that will come up in my talk several times through the central Glückstadtgraben. That gives you an idea about the resolution. We are looking at 6 seconds two-way travel time, means about 10 kilometers depth. So it's really a very good database due to this industrial interest. But what is also exceptional is that we have a lot of academic experiments as well that have imaged the deeper crust. So we know very well where the moho is situated, but we also know how the crust is heterogeneous in itself, with high velocity areas and low velocity areas and so on. Then we have also tomography experiments and receiver function experiments, and we have gravity that we can use to close the gaps between all these different sections. So we can really go for a really well-constrained 3D structural modeling. And that's what the modeling then can result in. This is the Central European Basin System model. It resolves basically the resolution to the right that you see here. And the model is also openly available and can be downloaded as individual grids if anyone wants to play further with them. You can see that it is reaching the lithosphere-asthenosphere boundary. It has an upper and a lower crystalline crust. It has pre-Permian sediments, the Permo-Carboniferous volcanics, Rotliegend, Zechstein, and then Triassic, Jurassic, Cretaceous, Cenozoic. So if we look at these components of this sediment fill in detail, we can learn a bit how the basin has evolved. And let me start from the basement. So this is the crustal basement of the Central European Basin System. You can see we have Baltica in the northeast. This is the area that is Precambrian consolidated. We have a boundary that is striking roughly northwest-southeast, the Tonquist zone, that limits Baltica against Phanerozoic Europe that consists in the west of eastern Avalonia that has collided with Baltica first, and then we have the Variscan domains to the south. And all this puzzle is basically composing the basis of the Central European Basin System. So how did it all start? About 300 million years ago, the Variscan orogeny was complete. We are supposedly having an Himalaya-like topography with a deep foreland in the north. And this is what is left of it today. So the Harz Mountains are not so high any longer. And well, the 300 million years obviously didn't go without a trace. What happened in between? So let me start with the first layer that we have. That is the thickness of the pre-Permian, partly already metamorphic sediments, including the Variscan foreland that have been deposited before 300 million years ago. It's interesting to see that we have actually preserved the entire Variscan foreland. You can see this arcuate form that looks very much like the Molasse Basin today, just a little bigger. And in total, we have up to 14 kilometers of thickness of this unit. We also see in the Oslo Graben a thick part of local thickening. And that's basically sitting there below what we call the North German Basin. This layer is limited upward by a structural surface, the top pre-Permian surface that you see now in the upper left. And you see that this surface is up to 13 kilometers deep as well. And if we fill the holes in this surface, we get the thickness of the Permian Cenozoic fill from 300 million years up to today in total. You can see there comes another 12 kilometers, up to another 12 kilometers of deposits on top. And these two units basically also correspond to two tectonic megacycles. If we look a bit closer at this thickness map of the Permian to Cenozoic Basin fill, we see that there are two major directions, one northwest-southeast direction that follows especially the Polish Basin, the Norwegian-Danish Basin, and a more north-south oriented direction that is traced by the Glückstadtgraben, the Horngraben, and parts of the Central Graben. The same we can see, same two directions we can see also in the base of the Permian Cenozoic Basin fill. And we see again this northwest-southeast direction, of which I've already been speaking. In the north, the one that limits basically Baltica against the south, has always continued the development of the area ever since. And we have the younger elements of the north-south direction. So let me come back how it all started. At 300 million years, we know we had an intensive volcanic phase. There were a lot of volcanism, and we know we had a high topography. And both these observations tell us that we had to deal with a very heated lithosphere. That also means that it's actually nothing been preserved of this time slice, because the area always was above the erosional level. Only when the system started to cool and the thermal anomaly began to decay, the subsidence of the region has been preserved. So if we look at the thickness of the volcanic record that we know from wells, that you see on the left side. You see that there's up to 3 kilometers thick volcanic sequences that have been drilled. We have a bit of a dominance of the north-south direction, and we see that the volcanism affected a large area. We don't know how much it was initially, but this is what we see as having been preserved over the million years. Above the volcanics, there is an erosional unconformity, and the next younger or first sedimentary depositions, the Rotliegend, have been dated as 266 million years. So there's quite a time gap between the major volcanic activity and the first depositional recording, which tells us that probably there was deposition, but it's not preserved. So these Rotliegend sediments are then the first unit documenting that on the starting thermal subsidence. The Rotliegend was a dry river landscape where we deposit clastic sediments, mainly sandstones, siltstones, and claystones. And we see that the depositional area is again following the northwest-southeast direction. Largest thicknesses of more than 2 kilometers are preserved in the North German Basin, but also quite some Rotliegend is sitting in the Polish Basin and in the Northern Permian Basin area. After this, a first catastrophic flooding, global sea level rise, the Zechstein Sea enters, and then it evaporates at least 5 times. We get this succession of salt, 5 times on top of each other, with the copper shale and the basal conglomerate only in the lowermost cycle. And if we reconstruct the initial distribution of the Zechstein thickness, it looks a bit similar like the Rotliegend Basin. It's a bit larger if we compare the two. So the Zechstein subsidence is stepping over the margins of the Rotliegend Basin, but the center is still in the North German Basin, and the deepest areas probably are in the Polish, in the North German, and in the Norwegian-Danish part. Of course, the salt is not looking like this today, and to the right you see how the salt is looking today. So today we don't have 2.5 kilometers of salt in the basin center, but we have salt walls that are up to 9 kilometers tall. We see also that the salt structures follow the same structural trends that we have seen already in the pre-Permian surface. So we have the northwest-southeast oriented salt structures, and we have the north-south oriented salt structures. Why is this so? Because salt is a very special rock. It's less dense usually than other rocks. It deforms ductilely over geological timescales. We say it flows, and it likes to move if its hydrostatic equilibrium is disturbed for whatever reason. In moving, it controls the synkinematic depositional geometries and deforms passively also its cover layers that have been deposited pre-kinematically. It in the end forms salt pillows, salt diapirs, and salt walls. But it's also important because it has a few properties that makes them different from other rocks, such as its high thermal conductivity. So for the geothermal exploration, salt is extremely important because it acts as a thermal chimney. It's hydraulically impervious, which makes it a super place for storing stuff we want to be safe, like, for example, green hydrogen in caverns of salt, or increasingly discussed, or since a long time discussed and disputed as well, nuclear waste. If we look at the topography of the Zechstein salt below the North German Basin today and plot it at the same scale as the Alps, you can see that the topography is impressive. I have this figure always for my students because they cannot imagine how big such salt structures can look like. But of course, this appearance is the summary response of salt to several deformation phases. It's not all happened at once. It started with the Triassic extension. So after the Rotliegend and the Zechstein thermal subsidence is slowly decaying, we experience a phase of extension, and we open the big grabens of the North German Basin, the Glückstadtgraben, the Horngraben, for example. The Polish Basin and the Norwegian-Danish Basin stayed true to their Tornquist zone and still are northwest-southeast oriented, so maximum thicknesses and deepest parts are here in the northwest direction, but the new element is that in the Triassic are the grabens. and they can have up to 7 kilometers of Triassic sediments. It's easy to spot that the Glückstadtgraben is, of course, connecting to the salt walls beneath Schleswig-Holstein. If we look at the cross-section that I have been showing earlier today already, and this is the place where the cross-section is running, the seismic one, we can see the extreme thin kinematic thickening of the Triassic unit, which is the pink unit here in this section, in the center of the Glückstadtgraben. We further see that the salt is almost removed in the center of the Glückstadtgraben to move into these salt walls, and that the salt layer is increasingly less depleted if we go towards the margin of the Glückstadtgraben. Interestingly, the salt sits there as it has been deposited beneath the East Holstein-Mecklenburg block. For whatever reason, this block obviously was very stable and has not deformed at all throughout the last 250 million years. The rocks we have in the Triassic are the classical Germanic Triassic with the dry river landscape of the Buntsandstein, the global sea level rise and marine influence of the Muschelkalk, and the Kuiper that switches between arid and more humid fluviatile deposition. In the Jurassic, differential subsidence continues, but now the northwest direction takes over again. So if we look at the thickness distribution of the Jurassic, we see up to 4 kilometers thick deposits in the Polish-Norwegian Basin, but also in the Lower Saxony Basin and in the Saltpeter Basin and in the northwest striking parts of the Central Graben. That this is the case, we can also see in a few seconds in a section, but first let me summarize that again. We have shallow marine fluviatile intercalations, deposit claystones, sandstones, and marls. But over large areas, these rocks have been post-depositionally eroded. So you see in the thickness map this huge white spot in the central North Sea that Mr. Underhill has termed a thermal dome, the origin of which is still debated. But looking larger over Europe, we see that there was an area of uplift, a period of uplift over large parts of Europe, the reasons for which we still do not properly understand. But we see uplift also in the northern parts of the North German Basin. This is also reflected in the record of the Jurassic in the section shown in blue, where in the central parts of the Glückstadtgraben, for example, there is very little preserved, either because the salt layer was depleted and there was no subsidence any longer here, or because the area has been post-depositionally uplifted and eroded. In any case, the layer of the Jurassic is limited upward as well by an erosional unconformity, which tells us that the area was above erosional level. In the Jurassic, we see, as I said as well, that in the northwest striking elements, we get an influence, a subsidence increase in the northwest structures. And if we look at the cross-section through the Lower Saxony Basin, that is shown here to the right, we see that we have synkinematic thickening of the Jurassic compared to other parts of the North German Basin. So this area is subsiding. And some people say it's subsiding because we have transtensional motion along the southern margin of the entire basin system. In the Cretaceous, this continues, as you can see in the same section in the lower right here, even more so. The early Cretaceous is a time when the Lower Saxony Basin experiences extremely accelerated subsidence, as you can see here with the synkinematic thickening. And then it is covered by Upper Cretaceous that's been deposited during a global sea level rise. Interestingly, the areas of the North German Basin didn't answer in the same way to the Cretaceous. So if we look at the northwest-southeast structures as the Lower Saxony Basin, we see that this area has been subsiding. If we look at the Glückstadtgraben, we see that this area was also subsiding, but not in a punctuated way. So the thickness of this green Upper Cretaceous layer is actually constant. If we would flatten that section to the to the base tertiary, we would have a constant thickness Upper Cretaceous. So this structure did not move during the Cretaceous. There was no salt motion. It only resumed after the Cretaceous. When the basin has been inverted, at the end of the Cretaceous, alpine tectonics, foreland stress transmitted to the foreland, caused inversion of large parts of the North German Basin, and the localization of this inversion was particularly prominent at the basin margins. So we have strong inversion along the Polish Basin, the mid-Polish swell. It's white here. The Cretaceous has been post-depositionally eroded. We see the Lower Saxony Basin, the Saltpeter Basin all popping up. We see the Grimmen High coming out. The Grimmen High is here. And it also brought us, it's the location of the section, it also brought us the beautiful chalk cliffs in the island of Rügen that you can see here. And that has inspired quite some arts in the past. Without the late Cretaceous inversion, Caspar David would never have made his romantic painting. So this uplift, as I said, focused at the basin margins. The strongest inversion occurred along Rügen, along the Harz Mountains, in the Osning, and in the mid-Polish swell. The next phase, we have a global sea level drop in the Cainozoic, but still subsidence continues after the inversion, but it moves to the North Sea. So we have about more than 3.5 kilometers of sediment deposited in the Cainozoic of the North Sea. But you can see also in the outer parts of the Glückstadtgraben, we have a few thickness maxima of more than 2 kilometers as well. So we reactivate, obviously, something in the Cainozoic. Also nicely visible in the same cross-section where you see this nice normal fault delimiting the East Holstein Trough with an offset of more, let's say, than, I would say, 1.5 kilometer. And you see that we have also reactivated the salt that started to move again and breaks its cover layers and creates thin sedimentary rim synclines, so-called. I think that's the tertiary version of the generations. So that we have normal faulting tells us that we have extension, that we have the salt crests rising again tells us that we have the salt responding to this extension as well. We have a river moor landscape alternating with shallow seas. We deposit our lignites and we deposit our rupelian clay, both resources in the North German Basin that have been quite valuable. And at present, the rupelian clay is especially important because it separates the fresh water above, which is our drinking water, from salty brines sitting below and being fed these groundwaters by all these salt structures in the subsurface that had quite some time to dissolve in the pore fluid. The final phase is, of course, the ice ages in the Quaternary. And these ice ages overprinted the previous succession by carving deep valleys into the previous units. And this is just a schematic profile from a drinking water aquifer in Berlin. But what it shows is that these glacial valleys have carved into their basal layers, and they may, for example, carve a hole into the rupelian clay and therefore provide pathways between the salty groundwater and the fresh groundwater. That's why we really need to take care of where these things are. So the 300 million years of history had quite some ups and downs. And what is the potential for today now that I promised in my title? So there are several resources and options in the North German Basin that are, of course, connected to subsurface utilization of all kinds. You can see there is a lot of shallow geothermal in the region that can be done. I think alone in Berlin, we have more than 20,000 shallow Erdwärmesonden. There is, of course, groundwater that we need to preserve and to protect. But there are also options to store CO2, as we do in some places in the North Sea. Continental Europe is still banned from CO2 storage. In some places, there are experiments done with hydrogen storage in case we can produce excess hydrogen from excess renewable electricity providers. Then there are different aquifer thermal energy storage technologies that have been started, for example, in the extra formation of the Triassic or in the Muschelkalk of the Triassic. There's, of course, deep geothermal that's being explored all over the North German Basin in different units. And then, of course, we have the salt, which is a resource in itself. And there are many, many important uses for the salt, not only to store stuff inside, but also to use it as a material. And the brines are increasingly interesting as well for their content in what is solved in these brines. Then exploration of the copper shale has revived at the basal unit of the Zechstein. And lithium is, of course, a thing that is quite attractive at the moment. And there may others coming as soon as we learn how to take the stuff out of these brines. I have just time today to focus on like two of these potentials. One is the deep geothermal, and also very briefly, don't worry, I will not be talking for a long time now, and the groundwater. So let me start with the deep geothermal and show you how we can use such 3D structures and simulations to find out where we should go for geothermal. So this is again a view of the model of the units, and that's the thermal properties that are in these units. And you can see that the Zechstein salt is really much more thermally conductive than the other layers. You can see that the Cenozoic is very poorly conductive because it's poorly consolidated. You can see that the crystalline rocks and the volcanics are more conductive than the sediments. You can see that the volcanics and the crystalline rocks produce more radiogenic heat than the sediments. So if we drop all this together into a 3D finite element code and solve the heat equation, the steady state in this case, what we get is a thermal model. And we can cut this thermal model to illustrate where the depth to the 100-degree isotherm would be to help us find the geothermal sweet spots. And you can see here that this temperature is reached at very different depths across the system. So the first thing you see is that the basin is warmer than the margins, which is connected to the low thermal conductivity of the sediments compared to the crystalline rocks close to the surface at the basin margins, but also to the thick lithosphere in the northeast where Baltica sits, which has a very, very deep lithosphere-asthenosphere boundary. So the average thermal gradient is very different from this area here. And depending on where you are, you may drill 2 kilometers to reach 100 degrees or 5 kilometers. So if you, for example, look at Poland, it's very important to know in which region of the thermal regime you are in your prospecting analysis. You can also see that the Netherlands are the hottest place in the North German Basin, and that along the Glückstadtgraben we may have over a lateral distance of 50 kilometers, maybe 1,000 meters difference for the same temperature. Let me switch now to another applied aspect, which would be groundwater. And for this, I go to the region of Brandenburg, where we have a higher resolved model because we had a better overall database, higher resolved. You can see that we have now also the quaternary discerned, the Rupelian, not only Cenozoic 1 unit, and also the Mesozoic units are higher resolved. So what we did here was to run a coupled thermohydraulic model and have assessed both the deep geothermal potential, but also what the groundwater regime in the subsurface of Brandenburg looks like. The reason why we were interested in that was if we look at the drought development over the past years, we see that Brandenburg is one of the driest regions of Germany. And on top, we see that we observe falling groundwater levels. So especially, this is a topographic map with all the groundwater level wells from the survey of Brandenburg, from LFU. And we have a time series of monthly resolution from 1976 to 2013. that show us that in areas of high topography, which are the green areas, we see red numbers, and that means falling groundwater levels. Whereas next to the rivers, we don't see that yet because we are so close to the river level that this is the last place that we'll see that the groundwater is falling. We also see that groundwater is being lost in the system from GRACE data. So this question was in the middle of our story to see, is this climate change? Is this anthropogenic effects? Why is this happening? Do we have a risk of upward saltwater migration? And what do we need to care about if we want to balance all these competing interests of geothermal, especially shallow geothermal, and groundwater safety? So the plan was we reproduce what we observe in the wells from 76 to 2013, and then use the method to test future climate scenarios. And this is just a few very brief results. So if we look at how the flow systems in the subsurface of the North German Basin looks like, and it's here for Brandenburg, it will be very similar also for the other parts of the North German Basin. We can see that we have deep flow systems, and this is the Buntsandstein aquifer down here. This is the Keuper-Jurassic aquifer down here. And those are of a longer wavelength and have a regional flow that is rather slow and goes towards the basin center because it goes with the slope of the layer and is deviated a little bit by the salt structures. If we look at the shallow flow systems in the Cenozoic, where we have our drinking water, we have more local flow system, topography-driven catchments, and higher flow velocities and shorter residence times. So we use this model and have prescribed the measured recharge to see if we can reproduce what has happened in the last 50 years. And this is the map of the observed change, and this is the map of the model change. And please keep in mind, we did not include any anthropogenic effects. So what we see is we have less clustering, we have fewer wells with falling levels, and we have in general less spatial zonation. But on average, the fit is not so bad. So the approach is actually valid. And in some of the misfits, we see clear reasons for anthropogenic effects. So the green polygons they show the lignite mining areas of the Lausitz, for example. So ongoing work is looking at all these things in more detail and tries to project that into the future. And Michael Züppin is going to come up with new results on that soon. So to finish my talk, the North German Basin has a very rich history and much to offer. And it's really valid to go and explore why, what, and how much is to be found, but also to assess what happens if we extract or insert anything. For this, we need to build digital twins to test what-if scenarios. And I think I'm working on this since a long time. It's not the only thing I'm working on, but I'm still finding new questions to look for. Thank you for listening.